A second kind of reliability analysis lies in what's known as generalisability theory. Unlike true score theory, which assumes that there is one kind of error all lumped together, generalisability theory looks at all the separate sources of error, which are known as factors, and the interactions between them. These fall into a number of categories, which I'll explain in more detail in a moment. It's a bit like analysis of variance as opposed to t-test comparisons of means compared to true score theory. It may seem a little difficult to get one's head around, and a good example can be seen in a popular television programme, Strictly Come Dancing. In this, there are a number of different components. There are contestants, and it is the contestants between whom you wish to distinguish. There are judges, and the judges include the general public, of course. And then there are tasks, and these are the different kinds of dances. So these are the sources of variance. But there are also interactions between each of these. So there are interactions between the judges and the contestants. Some judges may like some contestants better than others. This is particularly important with the public as a judge, who tend to take to particular individuals even if they blatantly cannot dance. There are also interactions between judges and dances. Some judges may be expert in modern or Latin and therefore are less expert at assessing other dances as they take place. There are interactions between the contestants in dances. Some contestants are just better at some styles of dancing, such as old time, compared to other styles, such as rumba, for instance. And then finally, there'll be an interaction between all three, contestant with judges with dances. So these are all the sources of variance which can be analysed in a generalisability analysis. Let's have a look at this applied to a real-world setting, to a short OSCE with 3 stations, and in this trial there were 3 candidates and 3 judges. We should say from the beginning that the overall value of G at 0.76 is a high value. G varies between 0 and 1, as does Cronbach's alpha, of course, and other measures of that kind. So we know that overall this is actually quite a reliable test. But when we analyse the relative contribution to variance, what we find is that the biggest single source of variance is in fact the judges, significantly greater than the variance due to the candidates. This may seem surprising, but in fact is something which emerges really very frequently in assessment of high-performing individuals, that variance comes more from the judges than it does from the applicants or candidates or students or trainees in medical settings, and it's something that we have to bear in mind when looking at the outcomes of examinations. The variance between due to cases is relatively small, but the variance of judges with candidates is also significant. So we can see if we look at the variation between judges and judges with candidates, together they represent significantly more than 50% of the total variance, which is something which might cause some concern. Judges with cases and candidates with cases makes no significant contribution to variance, and judges with candidates with cases has a small component. The really major ones are the judges with candidates, and the candidates. Now we can also carry out what's known as a D study, a decision study, as to what will happen with G as we change some of the elements of the test itself. And here we're going to consider an OSCE, and at the top line we're going to look at one particular OSCE where we increase the number of judges sequentially. What we can see is that with one judge, reliability of one OSCE station was 0.46, which is singularly unimpressive. We would normally like to be over 0.7 or even 0.8 for a high stakes exam. If we add a second judge, then the reliability increases, but it does not increase by very much. And even if we went up to 6 judges, it's only increased by a relatively small amount and not enough to reach the values that we would want for a reliable assessment. So the temptation just to increase the number of judges is rarely justified. However, if we look at the impact of increasing the number of stations, then we can see that this is dramatic by comparison. Going to 2 stations, each with 1 judge, there has been a significant jump in the overall reliability, And each time we add a station, 3 stations, 4 stations, 5 stations, 6 stations, then the reliability increases. By the time we get to 3 stations, we've passed the 0.7 mark. By the time we get to 5 stations, we've passed the 0.8 mark. Now, this is based on a particular example, but it's frequently observed to be the case. There is a small increase in reliability by increasing the number of judges, but a much greater increase in reliability by increasing the number of challenges, the number of items, the number of stations in an OSCE, or the number of questions in an exam. And this is a valuable guide to exam strategy. Double marking, as favoured by universities in general, is not a significant way of gaining an increase in reliability. I've graphed these values and you can see that the number of OSCE stations is significantly more useful than increasing the number of OSCE markers. And this represents a D study carried out from one of the Royal Colleges, although they would not allow me to say which particular college it was. And you can see that as the number of stations increases, so the reliability increases as well. And it crosses the 0.7 line around about 12 stations. It crosses the 0.8 line around about 17 or 18 cases. And they actually used this D study to decide how many stations they should have in their overall OSCE.